Hey guys, this is Mr. Sal. This is a lesson on scientific notation, just some basics. There is a formal scientific notation, so we have to be careful with how we write some of these numbers. But it is just a way, generally, to write very, very large numbers or very, very small numbers in a very quick way using base 10 values, which is kind of just like its place value. So this would be kind of a formal definition for scientific notation. I'm not really interested in that so much, and I'm sure you aren't either. What we really want to know is that we have a place value in the ones position, and then we have the decimal, and then you can have as many decimal places as you need, but it's always multiplied by some base 10 value to some exponent value. Now, the only thing about this ones position is that that value cannot be 0. And the exponent of 10, we have to be careful on that because sometimes it's negative, sometimes it's positive as well. So it could be one of the two, and it doesn't matter which is which. If it's positive, it generally means it's some kind of extremely large number. If that exponent is negative, then it usually means that we're dealing with some kind of small number. It does not mean that the value is negative. So here's some examples. Let's change these scientific notation numbers into standard notation, and we can see from these values that both of them have a not 0 number in the ones position, and then you have some number of decimals after that with the base 10 to some power, which is all we really need right now. Now for this 6.345 times 10 to the power of 8, this 8, since it's positive in scientific notation, that means it moves the decimal to the right. And in this case, it would move it right 8 places. So let's look at that value. I have the decimal after the 6, which is good in scientific notation, but I'm going to move it to the right 8 places. 1, 2, 3, 4, 5, 6, 7, 8. So this is where the decimal will be. And we have a bunch of empty place values which we need to replace with zeros. So this is what I have here. The actual standard notation, let's go ahead and write that in. And we'll throw some commas in there to make that a little bit easier to read. 634,800,000 would be the standard notation for that scientific notation. So what about B? This is another positive 4, which means we're going to move the decimal to the right from scientific notation, right? So let's look at 8.04 and move that decimal 4 times to the right. 1, 2, 3, 4. And again, we're replacing those empty place values with zeros. That's where the decimal will be. Not that we have to show it on this one, but we could if we want. That looks like it's 80,400 on that one. Not quite as big, but still big enough that it could be written in scientific notation. Next up, we got this standard notation at 5,320, but we want this in scientific notation. Looking back at what we remember from scientific notation on that last slide, the decimal has to come after or to the right of the first non-zero number. So this means that the 5 will need to be in the ones position, and the decimal will come after that 5. Now that takes care of the decimal portion of this, 5.320, and since 0 is kind of just holding that place value, you could get rid of it. Some people would say that it has value depending on how large the number is or what values you're comparing it with. For us though, we're going to get rid of it because we don't need to show it. And then this is going to automatically be multiplied by some base 10 value, but we've got to figure out the exponent. So this is a large number, or it's a number that's not a decimal. So this means that the exponent will be positive. How positive will it be? Well, that's where the decimal was for 5,320. And then we move the decimal 3 times to the left, which means that the exponent would be a positive 3. Now we don't have to show that positive there, of course. So 5.32 times 10 to the power of 3 would be the correct answer, and you could check this. If you plug this into a calculator, you'll get the same exact standard notation number. So this brings us to 420,000. And again, the decimal would be right here, even though it's supposed to be for scientific notation after the 4. Right? We got a value in the ones position, so that'd be 4.2. And again, I don't need to really show those zeros there. This would be multiplied by 10 to what power? 1, 2, 3, 4, 5. And is that 5 positive or negative? Well, since that 420,000 is bigger than 1, it will remain a positive exponent. All right, let's go ahead and try these values. They gave us a couple examples there, which we don't necessarily need, but hopefully they'll help us as long as we can look there at the bottom. I'm going to move that, but that would be what formal scientific notation would look like. Now the big difference between these numbers, if we look at the standard notation, is that these values are less than 1. Therefore, our exponents are negative, like this. So going from standard notation to scientific notation on these ones, it is a little bit different. Let's look at the number. So it looks like I have 7,500 thousandths, and that's good. So where is it that the decimal needs to be? It should go to the right of the first number that is not 0, which in this case is 7. So scientific notation will make this 7.5 multiplied by some base 10 value, and since this original value is smaller than 1, it's going to be a negative exponent. How negative will it be? Well, we move that decimal 1, 2, 3, 4 decimal places, so that would be to the power of negative 4. Well, what about this next example? So again, the decimal should go to the right of that 4, which would give us 4.005. And this would still be multiplied by 10 to some power. We just don't know what power it is. However, that value is less than 1, so we know it's automatically going to be negative. How negative will it be? 1, 2, 3 place values it was moved. Therefore, it would be an exponent of negative 3. All right, this next example, a 4.2 times 10 to the power of negative 8. We got that 4.2 right there. And since that exponent, this in a different color, that exponent is a negative, that means we'll move the decimal to the left of the scientific notation. So moving it left, how far? Well, that exponent was an 8, so we'll move it to the left 8 times. 1, 2, 3, 4, 5, 6, 7, 8. And I didn't give myself a lot of space there, but we can still fill in zeros. 1, 2, 3, 4, 5, 6, 7. So I'm going to write it out with a 0 in there in the front, so that'd be 0. Looks like there's 7 zeros. And then we had the 4 and 2 there. Now you could have plugged that into a calculator. It would have given you the standard notation number, and you would have had it right there. And that's okay as well. The next problem gives us 8.12, and then this is a power of negative 7. So we are moving this one to the left as well. How far to the left? That was a 7. So we're going to move it to the left 7 decimal places. 1, 2, 3, 4, 5, 6, 7. So that's where the decimal will be, and we can replace all those empty place values with zeros. So writing it up here, I have 0. Looks like there's 6 zeros there. 1, 2, 3, 4, 5, 6, and then we had the 8, 1, 2 as well. So that would be the standard notation for this decimal value. This first part, express 4,532,344 in scientific notation with 3 significant figures. Alright, that means we only want 3 numbers, which includes the ones position. And if we look at this number, we're just taking the three numbers farthest to the left, not 0. So, starting with the non-zero number, that's a 4, 5, and 3. Now we could look to the 3 and round that, but the 2 is going to keep that a 3. And the decimal would go after the 4. So right now I've got 4.53. I will multiply this by 10 to the sub power. And how many times would I have moved that decimal? It would have been after this 4 in the ones position. And then it would have moved to the left 1, 2, 3, 4, 5, 6 times. And then to consider if that exponent is positive or negative, the original number is bigger than 1. Therefore, the exponent is positive. And that's all we need to do right there. The next problem will work the same way. I'm looking farthest to the left for my first not zero number, which is 4. And we want two significant figures. So I'm going to round the 5. And since the 3 is less than 5, it will stay a 5 in that position. So I'm going to have these two numbers as part of the scientific notation. 4.5. Still multiplied by 10 to some power. What power would it be? That number is less than 1, so it's negative. And then we just look at how far we move the decimal. 1, 2, 3, 4 times. So that is 4.5 times 10 to the power of negative 4. Alright, why are these two numbers not in formal scientific notation? That is because this decimal has 3 numbers to the left, therefore it is not in scientific notation. This number has only one number to its left, but it's a 0, which cannot happen, so that is why that one is not in scientific notation. This problem is multiplying these two numbers, and the nice thing about scientific notation, especially with these really large numbers, is we can calculate operations very quickly with them. So here's what I'm going to do is, we don't even need the parentheses on these. And that is because everything here is multiplication. So the order of operation is going to be the same, and we can use the commutative property of multiplication to move these around, which is what I'm going to do. So I'm going to move like factors here, or multiples next to each other. For example, the 8.2 is like the 8.1, and those are multiplied. But I have 10 to the power of 33, which is like base 10 to the power of 16, and those are multiplied. Of course, it's all multiplied, but what this does is it allows me to multiply just my constants here, which would be 66.42, and then my base 10s, since I'm multiplying the bases, which are the same, I can take the exponents and add those together, which ends up being 10 to the power of, looks like 49 right there. So right now I have 66.42 times 10 to the power of 49. However, 66.42 is not in formal scientific notation, because the decimal needs to be after the, or to the right of the 6 farthest to the left. So I know it's going to be 6.642, and yes, we'd multiply that by some base 10 value, but the moving of that decimal makes that 66 a smaller, just 6 value, which means that I've got to make my exponent a bigger value. So the 66 became smaller by 1 decimal place, so I've got to make my exponent larger by 1 decimal place, which would give me an exponent of 50. And that would be the answer right there. So this one's going to work the same way. Parentheses or no parentheses isn't important. I'm going to take my 1.4 and my 8.5 and move them closer together with multiplication. Then I've got my base 10s. Base 10 with a power of negative 36 and also a power of 31. These are multiplied. But they're all multiplied, so let's go ahead and multiply the 1.4 and 8.5. And that gives me 11.9. Of course, I've got my base 10s here. 10 to the power of, that'd be negative 36. And they're multiplying the same bases, so we're going to add the other exponent, 31. These are multiplied. So I've got 11.9 times base 10 to the power of, that would be negative 5 right there. But once again, I've got that 11, and I need to change this to 1.19, which means I'm going to move the decimal one place. Since I'm making the 11 smaller into a 1 value, I'm going to have to add 1 to the exponent. So this ends up being 1.19 times 10 to the power of negative 4. And that would be my final answer right there. Right, division is going to work the same way. I'm going to split this up into two separate problems, which means I've really got 1.92 divided by 1.6, which I can put into the calculator, and that would give me that value at 1.2. Well, I've got my base 10s, and since it is dividing the bases, which are the same, 10, I'm going to take my exponent from the numerator, negative 11, and subtract the exponent in the denominator, which is negative 3. So that's 11 minus negative 3, which really becomes plus 3 right there. So it's 1.2 times 10 base to the power of negative 8 now. And that's as far as we can simplify that one to this point, because we have the 1 in the ones position, and it's not a 0. There's no other values in the hundreds or thousands and so forth. So that's as far as we need to go. This one is going to work the same way. So I'm going to take my 1.265 and divide it by 5.5 in my calculator. That gives me 0.23, which we'll address later. Then I'm going to look at my base 10s, and we are dividing the base 10s, so I'm going to take my exponent from the numerator and subtract it from the exponent in the denominator, which is negative 26. And so I've got my base 10, negative 63, that's going to be plus 26, gives me an exponent of negative 37. Now in this one, I've got 0.23. I don't want the 0 there in the ones position. I need the 2 to be there, which means I'm going to move the decimal to the right one place and make this 2.3. It'll be multiplied by the same base 10, but since I made that small number, that decimal value, a bigger 2.3, I'm going to have to subtract 1 from the exponent. So negative 37 minus 1 would be negative 38. And that right there would be my final answer for this one. Alright, that does it for this lesson. Thanks for watching, you guys. If you liked it or if it helped you out, please like the video and subscribe to the channel and comment about the video below. Thanks for watching.